Hello everyone, welcome. I heard your complaints, so we're redoing the weather theory video, this time with much quieter background music. Indeed, it is a long one. My goal was to create one single reference video you can come back to if you needed a weather refresher. I'd love to hear from you. How far did you actually make it into the video before tapping out? And how many times did you have to rewatch a section before it clicked? Timestamps are right here for my fellow skippers and ADHD folks. Here are some references. And if you're interested in your backyard, everyday, small-scale weather, I would highly recommend this book. It's a perfect companion for what we're doing in this video. Let's start putting the weather puzzle together with our first piece, our thin blue veil, or the atmosphere. Our atmosphere is made up of nitrogen, oxygen, with other trace gases like CO2, hydrogen, ozone, and methane. We say that our atmosphere is 78% nitrogen and 21% oxygen, and leave out everything else. As we go up in altitude, those percentages stay the same, but the overall pressure of the gases decreases. When we have humid days, our nitrogen and oxygen percentages change slightly to make way for water vapor. Believe it or not, water vapor is in the atmosphere pretty much all of the time. It makes up anywhere from 0 to 4% of the atmosphere, and a really humid day is about 3% water vapor content, or about 4% in tropical climates. Our atmosphere is separated into 5 different layers based on their chemical composition, temperature variation, and density. Most of the weather is in the troposphere. That's the lowest layer of the atmosphere. It extends up to about 12 miles or 60,000 feet at the equator, but around the poles it only goes up to 4 miles or 23,000 feet. This height difference is due to temperature variations, with the equator being the hottest and the poles being the coldest. The most defining characteristic of the troposphere is that temperature and pressure decrease with altitude. At the top of the troposphere is the tropopause, which is a boundary layer that separates the troposphere from the stratosphere. And this is also where jet streams are found. The second layer of the atmosphere is the stratosphere, which continues up to about 160,000 feet in altitude. There is little to no weather here, unless intense thunderstorms make it through into the lower parts of the stratosphere. The air is generally stable, and temperature actually increases in height. And this is because of heat that gets released as part of ozone formation. At the lower levels of the stratosphere, you'll find airliners flying above the weather around 35,000 feet in altitude. Unless you become an astronaut or launch amateur rockets, you won't have much use for the mesosphere, thermosphere, and the exosphere. The main story here is that as we go higher and higher up, there are fewer and fewer and fewer air molecules, and eventually they're spread so far apart that we call it space, since that's the majority of what's left. Back on Earth, for weather to happen, we need energy. All of our energy comes from the sun. Fancy new word, insolation, incoming solar radiation. When that energy gets to our planet, some of it gets absorbed by the atmosphere or is reflected back by the clouds. About half of it gets to the Earth's surface. If you remember middle school science, radiation, conduction, and convection is how energy is transferred. Radiation is how we get energy from the sun to warm up the ground. The ground in turn transfers that heat to the air above it through conduction or direct contact. And you've probably heard that warm air rises. That is convection, or heat transfer in a fluid or in air. And the reason warm air rises is because warm air is less dense than cold air. A good example of that is boiling water. You can see water get hot, rise up, cool off, and sink back down. And the same thing happens with air, we just can't see it. The reason I'm mentioning radiation, conduction, and convection is because all weather on Earth either causes a heat transfer or is a result of heat being transferred. And those 3 ways are how that happens. The reason we have weather in the first place is because of uneven heating of the Earth's surface. There are a couple ways that happens. You know how you feel hot when wearing dark colors? That applies to our planet as well. On a global scale,
a dark forest will absorb more heat than snow-covered ground. On a smaller scale, a parking lot will be much warmer than a field. That's uneven heating. A slightly different way that we get uneven heating is by tilting our planet. In case you didn't know, the Earth is tilted 23.5 degrees in relation to our orbit around the Sun. The Earth maintains this tilt year-round, but different parts of the planet get exposed to the Sun a little bit differently throughout the year, and this is what causes uneven heating, or as we call it, seasons. In the summer, the northern hemisphere, the half above the equator, is tilted towards the Sun and receives more concentrated sunlight per area than the southern hemisphere does. And the opposite is true in the wintertime, when the northern hemisphere is tilted away from the Sun, and that same sunlight is more spread out, meaning less sunlight per area compared to the summer. The tilt is also why winters and summers are opposite in the northern and southern hemispheres. You might not have thought about this very much, but I'm sure you've noticed the path the sun takes during the summer and the winter is different. If you think of why that is, now that you know the planet is tilted, it kind of makes sense, doesn't it? There are a few interesting examples of what happens because of this tilt, and this happens usually around the summer and winter solstices. Because of the 23-degree Earth tilt, the solar rays will hit 23 degrees of latitude at a 90-degree angle during the summer solstice. And it looks like somebody turned the shadows off.
Photos and videos taken during this time seem eerie, almost photoshopped, because there are no shadows.
At the same time, in the Arctic Circle, the sun will shine past where the Earth rotates, and that part of the globe is illuminated 24 hours in the summertime. Now, the opposite is true at the South Pole, where the sun doesn't get into the Antarctic Circle, and there are 24 hours of darkness. And each of these phenomena flip-flop for the opposite solstice. Now you're starting to see uneven heating on a global scale because of the tilt. But we're just getting started. It does get more complicated. Let's imagine for a second that the Earth isn't tilted and it's not spinning, so we can simplify. In this imaginary world, the equator gets most of the sun and heats up the most, while the poles stay cold. Hot air at the equator rises, flows towards the poles, cools down, sinks, and then heads back to the equator along the ground. It would be like one big loop of air moving around the planet. In reality, the global air movement is 3 different cells, mainly because the Earth is spinning. Our planet spins from west to east, fastest at the equator at about 1,000 miles per hour, and not at all at the poles, it's just spinning in place there. Now, picture air rising at the equator and heading north. That air is moving eastward with the 1,000 mile per hour initial velocity. But as it travels north, the ground under it spins slower and slower. The air isn't attached to the ground, so it keeps its original speed and outruns the rotation of the Earth, or veers right from a perspective on the ground. This veering, or turning to the right, is what's called the Coriolis effect. It's why the ideal air circulation loop breaks into 3 smaller ones. The same thing happens with air flowing back south from the poles. It starts with no eastward speed, but as it heads towards the faster spinning equator, the ground outpaces it. And once again from the ground, it looks like the air veers to the right thanks to Coriolis. Like I mentioned before, instead of one giant airflow cell, there are actually 3 different cells. Let's look at how the air flows along the ground in each one of those. Normally, it would flow from the south to the north or north to the south, but because of Coriolis, it's turned to the right. So in our polar and equatorial regions, air flows from east to west, but in the middle cell, the air flows from west to east. And these are our prevailing winds in those latitudes. And this is why in most of the US, our weather comes from the west. I also want to point out that the Coriolis effect is more pronounced over large distances. If you miss your 3-pointer or half-court, it's definitely not Coriolis. Overall, our entire global system does move from west to east, but the smaller 30-degree latitude chunks have their own circulations and prevailing winds within that west to east motion, as you can see in this time-lapse. The wind patterns and Coriolis effect are opposite in the southern hemisphere. This is why hurricanes will spin the opposite way on the other side of the equator, and so do high and low pressure systems. The reason we have different pressure systems in the first place is because of uneven heating. Our atmosphere is always trying to achieve equilibrium, meaning the same pressure and the same temperature everywhere. As it's trying to do that, we experience the changes as weather. Let's talk some basics. Cold air is dense, and because it's so dense, it has a high pressure. Hot air, on the other hand, is less dense with lower pressure. And you've probably experienced this at home. If you open a door or a window and it's cold on the other side, the cold air rushes towards you and just smacks you in the face. But if it's hot outside and you open the door, you don't feel the heat until you step outside. Weird, right? Keep this in mind for when we talk about how air masses behave when they meet. When it comes to pressures, I think of them as hills and valleys. High pressure air always wants to flow towards a low pressure. If we didn't have the Coriolis effect, it would go directly from the high to the low, but because of the Coriolis effect, high pressure air turns to the right as it's leaving the high pressure area, and it ends up rotating clockwise around the high pressure. As the air travels towards the low, once again it turns to the right, unable to go directly to the low, and it ends up rotating counterclockwise around the low pressure area. I remember it as left for low and the other way for a high. Now when the air eventually gets to the low pressure area, it doesn't just magically disappear. It has to go somewhere, so it goes up. Air here is less dense, hence the low pressure, and that allows the air to rise. As air rises, it cools, and if there's enough moisture content, we get condensation and clouds. Usually, where there's a low, there is unfavorable weather and precipitation. At the high pressure, sinking dense air gets warmed and clouds tend to evaporate, and this is why there's usually good weather around the high pressures. Now, looking at this wind map, where would you guess the lows and highs are? Of course, I can't tell how close you are, but hopefully you were thinking something like this. Remember, it's left for lows and the other way for highs, and it does get a bit complicated when there's a few of these pressures together. Let's go back and revisit our air circulation cells. We can see that the air circulation creates a semi-permanent area of high pressure around 30 degrees of latitude and a low pressure area around 50 to 60 degree latitude. The sending air warms and dries at the high pressure, and this is why we see most deserts around the 30 degree latitude area. The low pressure lifts air up, which then condenses and forms clouds and rain, and this is why there are forests and green stuff around the 50 to 60 degree latitudes. Something else about these air circulation cells: the temperature gradient between hot and cold where these cells meet is substantial. This is where jet streams form around 30 to 40,000 feet at the top of the troposphere. Jet streams are high-speed winds that blow from west to east anywhere from 100 to 200 knots. They follow the hot and cold air boundaries and are the strongest in the wintertime, where the differences between hot and cold are the greatest. Realistically, you probably won't run into jet streams until you fly jets, but it's still good to know where they are since they push all of our air masses around. Air masses are large bodies of air that have similar characteristics like temperature and humidity. And when I say large bodies of air, we're talking hundreds of thousands of miles across and going up into the stratosphere. These are areas where air masses originate: A for Arctic, P for polar, and T for tropical. The C means continental and M means marine. The area where air masses originate gives them their characteristics, and the longer an air mass hangs out in the area, the more it becomes like the surface that is below it. As these air masses get pushed around, they carry their weather to a new region and get modified as they move around. For example, an Arctic air mass that's cold and dry can move over the Great Lakes and pick up moisture, which then leads to lake effect snow in places like Chicago or New York. That same air mass can go from Canada to the southern US and remain dry, but will get warmed up from below. If you're wondering what the heck air masses have to do with flying and why we're talking about them, just give me a couple of minutes. One important part of air masses is how stable they are. A stable air mass will resist vertical motion, while an unstable air mass will encourage it. And the way we measure atmospheric stability is what's called the lapse rate, or how quickly the temperature changes with altitude. The normal rate that we all know and love is 2 degrees per 1,000 feet. Anything above that can be considered unstable. And here's how this would play out. Imagine a parcel or a bubble of warm air that got heated up by the ground through convection. It's wanting to rise because warm air is less dense than its surroundings. If the air mass is unstable, or cooling faster than 2 degrees per 1,000 feet, our parcel of air can't cool off fast enough as it rises, and it continues to be less dense than the surroundings. It'll stay buoyant and keep rising and rising like a ball that you try to hold underwater. On the other hand, with a stable atmosphere, our parcel of air would cool off quicker and become denser than the air around it, resisting vertical motion and sinking back down. So with that information, an unstable air mass will have lots of motion in it. We can assume that an unstable air mass will have turbulence. If there's enough moisture through evaporation or sublimation, that unstable air will have clouds that look bumpy, like a cumulus cloud. The surface visibility in an unstable air mass tends to be better as well because of all the motion and mixing of the air. On the other hand, if the atmosphere is stable, we can expect almost no turbulence and flat, stable-looking stratus clouds. Sometimes with a stable air mass, the visibility is poor on the ground, since there's no mixing and the air is more stagnant. Air masses don't just sit there, they get pushed around by the jet stream. And where two air masses meet, we call that a front. Cold fronts are colder air masses replacing warm air. Warm fronts are warm air masses replacing cold air. Flying-wise, when you cross a front, that will always mean a different temperature and different wind direction. Picture this when you think of a cold front. Cold fronts typically move quick and bring the worst type of weather with them. The cold, dense air slams into the warm air ahead of it and forces it up into the atmosphere. The rising air cools and forms clouds, and this is the unstable air situation we talked about before. The air being forced up can't cool off quick enough and ends up rising higher and higher. I'll keep this portion brief, but I would recommend reading up on frontal passages and the type of weather effects that they have. The graphics here show the extent of weather and what you can look for. Before a cold front passes, you can expect to see increasing cumulus clouds. The temperature is warm and visibility is good to slightly hazy with light precipitation possible. As the front passes, the clouds become cumulonimbus or thick low clouds. The temperature will quickly drop because of heavy rain, thunderstorms, and gusty winds, and usually the visibility is reduced during storms as well. After the cold front passes, clouds will quickly dissipate, the visibility will improve, and the temperature will stay colder than before the front got there. The precipitation will also dissipate and the air will remain dry. Now, did you notice how the temperature and the wind direction changed after the front passed? You know why? Because it's a different air mass with different characteristics. Sometimes we can have a fast-moving cold front that can create a line of severe weather called a squall line just ahead of the front. And this is where thunderstorms invite all their friends over for a party, and it's a party you don't really want to be anywhere near. It can extend for hundreds of miles and be extremely difficult to circumnavigate, not to mention all the hazards we'll cover in the thunderstorm section. Now let's look at a warm front. Warm fronts are gentler than cold fronts, but they take their time moving through. The less dense warm air rides up a gentle slope and typically causes layered clouds that don't have much vertical development. Picture this when you think of a warm front. Side note, don't do that. The propellers don't really like that sand. With a warm front, High layered cirrus clouds become mid and then low layered stratus clouds as the front approaches. Warm fronts move slower than cold fronts and bring light precipitation and poor visibility. As they pass, the temperature gradually rises, the wind changes, and the stratus clouds remain after passage. With both cold and warm fronts, when the temperature is below freezing, the rain will get replaced by freezing precipitation, like snow, freezing rain, etc. Now another type of front is a stationary front. It has cold air on one side, warm air on the other side, and the forces happen to be just about equal, and that front will stay around for a few days. Usually the weather is more like what you would expect from a warm front. Rainy, cloudy, gray. Eventually something changes the balance and the front moves along. Finally, an occluded front happens when there's a faster cold front catching up to a slow warm front. And it's a little bit complicated because you have cool air being replaced by warm air that is then being replaced by the coldest of the three. And so the weather here is a little bit of a mixture of everything, depending on where you happen to be in those fronts. Let's look at a surface prognostic chart, and hopefully this will help you start putting some of those pieces together. The most obvious thing is the highs and the lows, the fronts, but I want to point something else out. You see all these black lines that kind of swirl all over the place. Those are called isobars, iso being equal and bar being the unit of pressure. So these connect equal lines of pressure together. Now something this can tell you is what will happen with the wind. So over here in the Iowa area, they are spread far apart, so the pressure changes gradually over a large area. But then when we zoom into the Montana-Canada border, the isobars are close together, so the pressure changes rapidly over a short distance, and you can expect gusty winds there. So if we look over here on the border, you have winds gusting 41, 24, 26, so they are gusty right where the isobars are. Now if we look a little bit over to the east, where the isobars are further apart, you don't see any gusting. Right here it's just at 12 knots. Right here it's 19 knots. And 11 knots. So the winds are more or less behaving when the isobars are further apart, and when they're close together you can expect turbulence and gusty winds. We already talked about this with the wind map, but highs, everything rotates to the right, lows to the left or counterclockwise. When we look at the fronts, let's pick this one over here, that's Oklahoma and Texas. So temperature here, you can see that in front of the cold front, it's warmer, so it's 0, -4, -3. Behind the cold front, it's colder because it's a cold air mass replacing warm air. And then if we find a warm front, it will be just the opposite. So up here in Canada, it's -16, -14, and then on the back side of that front, it's -3 and 2 degrees. So warm fronts, warm air replacing cold air. Here we have a stationary front, and you can kind of see that the cold air is on the east side or on the right side, trying to go left. Warm air is on the left side, trying to go to the east. And we have a stationary front that kind of hangs out here. Now if I scroll through the time here, you can see that that stationary front kind of sticks around a little bit, and then the warm front will take over in a couple days. Something else I wanted to show you is this occluded front. So we talked about that at the end. An occluded front is what happens over here. This is a perfect representation. We have a warm front that then is being caught up to by the cold front. And when the cold front catches, that becomes an occluded front, and that's what this little swirly thing is all the way to the low. Now, as you can guess here, all the isobars are jammed together. They're nicely, tightly packed. I bet if we turned on the winds, it would be very gusty, except, it's water, so you might not have stations there. Winds are 25 gusting 37. Not surprising with all the isobars being like that. This guy, 19 gusting 34, 19 gusting 30. So you get the point, you get the picture. Now that we've seen the chart, let's talk about clouds. Have you ever wondered how much a cloud weighs? This classic fluffy cloud weighs about 650,000 pounds and contains about 78,000 gallons of water. We're talking half a mile long by half a mile wide and about 3,000 feet tall, which is what a normal fair weather cloud is. Now I want you to think about that for a second. When you hear about fronts, updrafts and downdrafts, thunderstorms, think about how much force that is. And we're talking about just one silly little cloud. So now that I've got your attention back, how do you make a cloud? We always have water vapor in the atmosphere, but the water molecules need something to stick to in order to form droplets. Those little particles are condensation nuclei, and they can be carbon particles from smoke, salt particles from ocean spray, or even soil that's been blown away by the wind. This is where the water droplets start accumulating and getting bigger, eventually becoming a water drop. So yes, technically there's a tiny speck of something in every raindrop, and that's why you shouldn't be doing this. So then, if we have all this water vapor in the air, why aren't there clouds everywhere? That's an excellent question. The amount of water vapor air can hold depends on its temperature. Warm air can hold a lot more water than cold air. And this is why blowing hot air on your windshield or defogging a bathroom mirror with a hairdryer works really well. The reason it works is because the relative humidity decreases as the air warms. This relative humidity is the relationship between air temperature and the dew point. Once the air temperature reduces to the dew point, the air is fully saturated and can't hold any more moisture. At this point, any extra water vapor condenses out of the air in the form of visible moisture, like fog, clouds, or dew. Think of it like overfilling a cup. What spills over is the visible moisture once the temperature reaches the dew point. Now I know that can be a lot, so let me summarize a little bit. Clouds, fog, and precipitation form when the air is saturated, or at 100% relative humidity. At that point, water condenses out as visible moisture. This happens when the temperature is the same or lower than the dew point. And this means that the dew point is the temperature to which air has to be cooled in order to reach full saturation. In practice, what this means is that when you look at your weather reports, a small temperature dew point spread is a good indication that fog or low clouds are likely. The temperature and dew point meet at the surface, and this is where the extra water vapor condenses out. If the temperature dew point meet at a higher altitude, that's where the visible moisture happens. And we actually have a formula for that to roughly estimate cloud bases. On the written test, it's in degrees Fahrenheit, but in practice you can use 2.5 degrees Celsius per 1,000 feet. Here's a rule of thumb for the temperature dew point spread. If it's 2 degrees or less, fog and clouds are very likely. If it's 2 to 4 degrees, they're possible, and above a 4 degree spread, the fog and clouds are unlikely. Okay, so now we understand that we have to get the temperature cold enough to the dew point, and then we have visible moisture. So how do we cool air to get it to the dew point and condense out its visible moisture? Well, for one, we can have a warm air mass move over a cold surface. Air can also be lifted or forced to rise, or it can cool at night through contact with cooler ground. At night, the ground cools very quick. Air in contact with that ground will cool and reach 100% relative humidity and condense out as dew. And if the temperature is below freezing, it will condense out as frost. So to answer the original question, we don't have clouds everywhere because everywhere the temperature is not equal to or lower than the dew point and the air is not 100% saturated. Let's talk about cloud types. Not those ones. There are 4 basic types: low, middle, high, and clouds with vertical development. As you can guess, the types are based on altitude. The heights vary a little bit depending on where you are in the world, as we saw with the troposphere heights, but generally low clouds are below 6,000 feet, middle clouds are between 6 and 20,000 feet, and high clouds are above 20,000 feet. There are 3 main cloud shapes: cumulus, stratus, and cirrus. Cumulus are the classic cotton ball puffy shape, stratus are flat, and cirrus are thin, hair-like wispy clouds. And that's enough information to identify most of them. Low clouds are stratus and cumulus, sometimes cumulonimbus, nimbus meaning rain. Middle clouds are altostratus, altocumulus, and then high clouds are cirrus, cirrostratus, and cirrocumulus. Finally, clouds with vertical development are cumulus clouds that build vertically, like towering cumulus and cumulonimbus, and some of those develop into thunderstorms. Right now, we're singling out each different type of cloud. But in reality, they're usually bunched together and you might not be able to identify them like that from the ground or even if you're flying. And when you hear the term embedded, that's exactly what it means. The storm or clouds are embedded in one another and you might not be able to see it. On your METAR or your TAFs, you might see CB for cumulonimbus. And hey, now you know what that means. And the reason it's mentioned in the first place is because of the hazards associated with cumulonimbus clouds. Vertically developed clouds happen because of rising air currents, and that means turbulence. It also means potential lightning with all the friction, lots of water, maybe even some hail, plus gusty winds, updrafts, downdrafts. That doesn't sound like a lot of fun. And just remember how much this stuff weighs and the forces involved.
Since we're talking about clouds, let me mention cloud cover. Imagine you're a cloud measurer device sitting in the airport. You're on the ground looking straight up, and you see the sky split into 8 different sections. If you can see the entire sky, you would call that clear. If 1 or 2 of the 8s are covered, you would call that few clouds. 3 to 4 covered would be scattered. When it's 5 to 7 eighths covered, that's a broken cloud layer, and fully covered is overcast. The lowest broken or overcast layer we call a ceiling. So in this example, it would be 2,500 feet. If the equipment can't determine the lowest layer, it will be noted as vertical visibility, usually because of haze or fog.
And speaking of which, isn't fog just a cloud, but on the ground? Exactly. Visible moisture that begins at the surface is called fog. If it starts above the ground, it's called a cloud. Now, if you were paying attention, you know that to get fog, the temperature and dew point should be the same or very close to one another. You know how in the morning you'll see fog that only sticks around for a little bit and then it burns off? That's called radiation fog. I mentioned that at night, the ground rapidly cools and we get dew. What we also get is a temperature inversion with the warm air above and the cool earth below. The ground cools the air next to it, which reaches a dew point and becomes saturated. And this typically happens on calm, clear nights with no wind and some moisture in the air. So this is how radiation fog forms. Now in the morning when the sun comes up and starts warming up the ground, eventually that heat gets into the air through conduction, and as we know, warm air holds more moisture, so the fog burns off. If the wind picks up during the night, it will also destroy radiation fog. Similar to radiation fog is steam fog. It just forms differently. In this case, cold, dry air moves over warmer water, and as the water evaporates and rises, it cools and condenses, forming fog that looks like smoke. You'll see this a lot on lakes when the land is colder than the water. And when it's really cold, water vapor can directly form ice crystals and cause ice fog. It looks really cool, but it's super dangerous to fly through. Advection fog happens when a layer of warm, moist air moves over a cold surface. Advection means horizontal motion, and wind up to about 15 knots allows the fog to form and intensify. This is very common in coastal areas like the California coast, where a sea breeze blows moist air over the land. And with higher wind speeds, the fog lifts into low stratus clouds. If the fog stays over water, we call that sea fog. One other type of fog that relies on wind to form is upslope fog. When you force moist air up sloping terrain, the air cools and reaches the dew point, forming fog. And this can last a very long time as long as we have the wind and enough moisture in the air. This type of fog doesn't burn off like radiation fog, but it does stop forming when the wind stops. Just like with advection fog, a stronger wind will lift upslope fog into low stratus clouds. And just a word of caution when it comes to fog. When you fly above a fog layer, you can see right through it because it's, 50 feet deep or something. If you come in for a landing, you're now looking through thousands of feet of fog, which you obviously can't see through. Don't do that. And if you ever wonder what the difference is between mist and fog, fog has lower visibility. They're both the same thing. fog is just less than 5/8 of mile visibility. And why the weird numbers? Because it's based on kilometers, and that's the conversion. You know what this means when you see it in a METAR? It means you should be going elsewhere, or at least wait till the weather passes. If you picked up on the coding, there's a thunderstorm with heavy rain at the airport. Thunderstorms are some of the most violent types of weather that we see. To make a thunderstorm, we need 3 ingredients. We'll mix them together and bake for 30 minutes. Moisture is first on our list, and we can find it at our local ocean or neighboring lake. Water evaporates and becomes water vapor, and there's our moisture. Air instability is the second ingredient. If we move an air mass over a hot surface, it will warm from below. And this, as you know, changes the density of the air and makes it warm and less dense. Now, in a stable atmosphere, the air would rise until it cooled off to the temperature that's around it, and that would be the end. In our unstable atmosphere, where temperature decreases rapidly with height, the air continues to rise when given a push. Finally, we need a lifting mechanism. Whether that's a cold front or a mountain, once there's upward motion, we have ourselves the beginnings of a thunderstorm. A thunderstorm has 3 distinct stages. It all starts with the cumulus stage, where moist air is being lifted up. Because of instability, the air continues to rise and clouds start forming once the dew point is reached. The clouds continue to build into high towering cumulus clouds. In this stage, strong updrafts prevent any precipitation from falling. Everything is moving up, creating this growing, fluffy, bubbly scene. And the cumulus stage lasts for about 15 minutes. Eventually, the weight of all that moisture gets to be too much for the updrafts to handle. Water drops begin to fall as rain, or hail if they got high and cold enough. One way you can tell the thunderstorm has entered the mature stage is by rain at the surface. And this is the most dangerous stage of a thunderstorm, and here's why. Warm, moist air is still rising. Precipitation and the air that it's pushing down are descending. There is a lot of friction, chaos, and turbulence. So much so that there is lightning because of all the friction. Below the cloud, the air is rushing down and eventually hits the ground. It does have to go somewhere at that point, and so it spreads out, creating all sorts of fun side effects. Things like wind shear, roll clouds, microbursts, and you can have a big gust that can form a gust front. The mature stage lasts until the upward motion slows down. That can be relatively quick, or it could take a while if all of our ingredients continue to be present. Our storm now enters the dissipating stage, where downdrafts spread out and replace the updrafts. Rain and some wind usually stick around for a while as the storm settles down. One sign you can look for is the anvil at the top of the cloud. Without vertical motion, the top gets blown in the direction of the upper level winds. This might be obvious, but don't try to fly through, over, or under thunderstorms. They can go as high as 60,000 feet and will build way faster than the airplane is capable of climbing. And the general rule of thumb is to stay away at least 20 nautical miles, because that's how far we've seen hail get tossed outside of clouds. Some other hazards worth mentioning: turbulence, hail, tornadoes, terrible visibility, lots of water, icing. Also, smaller aircraft are usually not equipped with weather radar, so you don't know where the thunderstorms are. And when you say, "Oh, I can use my ForeFlight," that can be minutes behind, and that's assuming that you have a connection. One final note on thunderstorms. Lightning is guaranteed in a thunderstorm, otherwise it would just be called a storm. Your airplane is designed as a Faraday cage to discharge all the electricity to all those static wicks that you pre-flight. Hopefully, you're never close enough to get hit by lightning, but even if you do, it will scare you more than do serious damage to the airplane or to the avionics. Latent heat is something we don't really talk about, but it's a pretty important phenomenon. Anytime there's a phase change, like solid to liquid or liquid to gas, or the other way around, heat is either added or removed from the environment. For example, to evaporate water, we add heat, and to condense it back to liquid, you release heat. With thunderstorms, the water vapor is condensing and becoming liquid water. That heat is released into the atmosphere, adding more instability and lifting action to power the storm. Latent heat is also something that happens to you when you step out of the shower. The reason you feel cold is because the liquid water robs you of the heat to transform into water vapor and evaporate. The reason water in various forms falls out of the sky in the first place is because the droplets or the ice crystals get too heavy for the atmosphere to support them. Depending on how high the water goes and what the temperature is, the water may remain liquid or turn into ice crystals. Eventually it falls and the precipitation at the surface varies based on what the water fell through. And here's a little diagram to kind of illustrate that. Sometimes we have a temperature inversion, where temperature increases with altitude up to a point. Inversions are very common in valleys or polluted areas where the air at the top will act like a lid, keeping pollutants and warm air below. Now if we had rain that falls through an inversion, it might freeze and fall as ice pellets. So in my little diagram we have ice crystals that fall into warm air, they melt, they become water, and then they go into colder air closer to the surface, and they freeze and fall as ice pellets. Ice pellets are therefore an indication of a temperature inversion, and that freezing rain exists at a higher altitude. And this may or may not be a question from the written test. Now, a little segue before we move on to icing. Have you ever seen this? This is Virga. It's rain that falls but evaporates before reaching the ground. It does look pretty cool, especially when the sun hits it just right. Sometimes, though, Virga might be an indication of a microburst that's about to happen, but most of the time it's just evaporating water vapor hitting dry air below. You know what else looks really cool when the sun hits water droplets just right? Rainbows. Rainbows are actually circular. We just can't see the bottom half on the ground because the earth gets in the way. What doesn't look cool when the sun hits it just right? This! Let's talk about icing. There are three main types of icing: clear, rime, and mixed. Clear ice is clear because it freezes gradually and there aren't many air bubbles trapped in it. It's the more dangerous type of ice since it's denser and can form horns on top and bottom of the airfoil. Usually it's found in warmer environments where there's a high moisture content and larger water droplets. Rime ice is a lot more common, and you might hear it being reported in pyreps. The water droplets are smaller and freeze quickly, trapping air bubbles, and that's why the ice looks opaque. And the problem with this type of ice is that the rough texture can disrupt airflow over the airfoils. And as you might have guessed, mixed ice is a combination of both the ice types when the water droplets vary in size. Clear ice is the fancy stuff you get at sit-down restaurants, and rime ice is what comes out of your fridge. In either case, ice, snow, or frost should never be on the aircraft. There are airplanes certified for flight into known icing conditions, but those are airliners, turboprops, and weeping wing aircraft that you probably won't fly until later ratings, or if you win a couple lotteries and buy a fancy airplane. Now, the rule for all aircraft, you heard that right, all aircraft, is that you can't take off with any accumulation of snow, ice, or frost adhering to critical surfaces. The reason behind this rule is pretty simple. The aerodynamics get all messed up and the airplane doesn't fly well. Simple enough, right? Contamination disrupts the smooth airflow over the wing surface and decreases lift. So much so that you might not even be able to get airborne at your normal takeoff speed and will stall at a faster airspeed as well. Our propeller is a rotating wing, so less lift there equals less performance on top of the reduced lift on the wings. Ice adds extra weight. The extra weight and non-smooth surfaces add drag and maybe even some asymmetric roll for the ailerons. Ice can also block the air intake or ice up your carburetor, and that further reduces your performance. Now, of course, the worst time to figure all of this out is when you're close to the ground. Oh, and your pitot tube and static ports can also ice over, so now you're basically a test pilot on an icicle. NASA and the FAA did some testing, and they found that a coarse sandpaper consistency of ice on the wing decreased lift by about 30% and added about 40% drag. At larger accumulations than that, drag increased by 80%. So to summarize icing, don't fly into known icing conditions. That means visible moisture when the temperature is below 0 degrees Celsius. Use icing forecast charts and treat ice as you do the dentist. Just don't go over there. And if for some unforeseen circumstance you do have to land with ice accumulation on the airplane, use a faster approach and landing speed. Remember how I mentioned earlier that you shouldn't catch raindrops because there's something in each drop? If the water is pure, there are no condensation nuclei for the drops to start forming. This means that water can exist in liquid form well below freezing, actually down to about minus 40 degrees Celsius. A neat little experiment you can try at home deals with this supercooled water. If you take a bottle of purified water and put it in the freezer for a few hours, you can then tap or smack the bottle, which will make a nucleation site. Instant ice. It's a really cool experiment, but you wouldn't want your airplane to become a condensation nucleus. Now, these supercooled water droplets are also responsible for freezing rain, which has the highest accumulation of any ice type on the aircraft. And this is why ice pellets on the ground below an inversion layer matter so much. You know how when you're at the beach, there is always wind from the lake or from the ocean? Why is that? During the day, land is warmer than the water, and hot air rises over the land, flows out to the water, cools off, and sinks down, flowing back to replace the rising hot air. That's a sea breeze, and it's really annoying when you get out of the water. This cycle continues until the sun goes down and the land cools off. At that point, the water's warmer, and the airflow reverses, with prevailing wind being from the land at night, and that's a land breeze. If you do fly above a land and water boundary, you will feel the land and sea breeze at altitude as turbulence. Speaking of which, no one likes turbulence. Let me tell you why it happens, and you can do your best to avoid it, although sometimes it's kind of inevitable. Turbulence is irregular motion of the aircraft. It can vary from annoying little bumps to severe jolts, and the severity will depend on the size of the airplane. When you report turbulence or see it in a PIREP, the severity and frequency are reported. Light, moderate, severe, extreme, and then occasional, intermittent, or continuous are the categories. And then there's also CHOP, which is rhythmic, frequent bumps, like driving down the gravel road, which is mostly just annoying. So why the turbulence? What causes it? The main culprits are convective currents, called convective turbulence, obstructions to the wind flow, called mechanical turbulence, and wind shear. Remember our friend uneven heating? That's convective turbulence. We talked before about how different parts of the ground heat differently. All those different ground patches warm up the air above them, and that makes a lot of independent convective air currents. Some have more upward motion, some have less, and it makes for a bumpy ride, especially in warm summer months. This is why a lot of people either fly early in the morning or wait until the evening, or they go during the day and then whine about having to fly through thermals. Thermals, by the way, are defined as a rising air current caused by heating from the underlying surfaces. Unlike diamonds, thermals are not forever, and getting above them is usually doable. If there are clouds around, the turbulence stops above the tops of the clouds. That is, until you have to come back down and land, and then you're bouncing your way back to the runway. Most people don't think about sinking air. We keep talking about air rising, but it does have to come down somewhere. As you know, air rises, cools, condenses, and forms clouds. That's below the cloud. Around the cloud, air sinks back down to replace the air that was just rising. Both rising and sinking air contribute to turbulence. And as we talked about before, around stratus clouds, there is less turbulence and the air is more stable, but it's bumpier around cumulus clouds where the air is more unstable. And you know what else is unstable? Your approach, because the wind is doing some odd and weird things during your landing. Have you ever noticed how there are weird wind patterns around the airport, especially with higher wind speeds? All those hangars, fuel pumps, hills, and trees cause mechanical turbulence. They're all getting in the way of the wind. You mostly see this type of turbulence below the treetops or the roofs, and of course it hits you right as you're about to make the smoothest landing of your life. And the higher the wind, the further the gusts and the turbulence eddies travel. One thing you may also notice, if you compare the winds at the surface with winds at altitude, is that they don't flow in the same direction. And that's because of the friction with the ground up to about 2,000 feet. Above that altitude, the wind flows more or less parallel to the isobars and at a higher speed. And this is one of the reasons why winds aloft are not reported within 1,500 feet of the station elevation. If you ever decide to fly in the mountains, make sure to take a mountain flying course. It might not sound like a big deal, but there's a lot that goes on. What happens if the wind runs into a mountain? Imagine what happens when a stream or a river runs into a big rock. It's a pretty similar outcome. If there's moisture in the air, you might see a lenticular or lens-shaped cloud, or maybe a few of them. They look really cool, but they indicate turbulence and very strong winds. There might also be some clouds below and downwind of the mountain that are called rotor clouds, and they also indicate turbulence. Now, if there's little to no moisture in the air, you probably won't see much, but mountains still produce mountain waves that propagate well above and downwind of the mountain. I bring all this up because mountains are notorious for turbulence. The examples and the diagrams I show here show a singular mountain, but that's just not realistic. We have mountain ranges, valleys, random protrusions, and the airflow around those areas is not as simple as you may think. And it's also something you don't want to discover by yourself. So take a mountain flying course if you plan to go into the mountains. Now onto the worst type of turbulence, wind shear. This is a change of wind speed and or direction over a relatively small distance. Wind shear can happen at any altitude, and it can be horizontal as well as vertical. There are two main types of wind shear, convective and non-convective. Convective wind shear is associated with a thunderstorm passage. As you remember, thunderstorms are the worst type of weather, and they bring a chance for the worst type of wind shear, which we call a microburst. A microburst is a small-scale, intense downdraft of air that spreads out along the ground. The good news is that a microburst is relatively small in size, and it's short-lived. The typical size is less than 2.5 miles in diameter, and it's usually less than 1,000 feet deep. It can last anywhere from 5 to 15 minutes. The bad news is that the downdrafts can be as much as 6,000 feet per minute. Also, the wind shift from one side to the other can be as much as 90 knots. Oh, and there's severe turbulence, of course. You'll see this illustration quite a few times in your piloting future. This is how a quote-unquote ideal microburst event would look. Imagine you're flying a normal approach and you run into a microburst. At the beginning here, as the airplane flies into the headwind in the microburst, performance increases. You end up getting more lift and more flying airspeed, and that takes you above your intended approach path. So what do you do now to get back on approach? You lower the nose and you reduce the power. As you get to about halfway through the microburst, the performance tapers off and dramatically decreases as the airplane now flies into a tailwind. Now you've lost a bunch of lift and a lot of airspeed. And what configuration are you in? You're nose down and low power. And that's a terrible combination with an increasing tailwind and decreasing performance. Meanwhile, this is all in pretty bad turbulence and being tossed all over the place with the ground getting closer and closer. Now, imagine this in your typical training aircraft. You're probably flying the approach at 60 to 70 knots or so. You might pick up and then lose 30 to 45 knots entering and leaving the microburst. Imagine losing 30 knots on approach while descending at 6,000 feet per minute. That's how you end up like the airplane at the end here. Don't forget that you're also probably being shaken so violently that you can't even see your instruments at this time. So how do you avoid a microburst? Look for thunderstorm activity, intense rain shafts, and Virga that I mentioned before, that rain evaporating before reaching the ground. Basically, the main point is don't fly near thunderstorms. Now, non-convective wind shear is not associated with thunderstorms. It's all about the wind changing speeds and or directions in relatively fair weather. Usually, it's a larger area that's affected, and it can last for quite some time. One of the signs of non-convective wind shear are temperature inversions. In an inversion, the air below is calm, while above the inversion, the winds just keep on blowing. The stable air allows the two to stay separate and not mix. And when you climb or descend through that area, that will subject you to wind shear. Another sign of non-convective wind shear is frontal passage. You already know that wind shifts across the front, so don't be surprised when you run into some of that. And then another one is crossing from land to water or water to land because of those land and sea breezes. Non-convective wind shear is typically called low-level wind shear. In fact, there are forecast charts that will show you an air met for widespread low-level wind shear. At larger airports, with the detection equipment installed, ATC and the ATIS will broadcast low-level wind shear alerts.
Attention aircraft, runway 2 left and right departure and arrival, wind shear alert, 15 knot loss on the runway, wind 26042, gust 50.
And you can also find that information in the METARs and TAFs, but usually not at smaller local airports. Here's what a TAF would look like, both for convective and non-convective wind shear. With convective wind shear, if there's a chance for thunderstorms and cumulonimbus clouds, you can expect convective wind shear. And you can see the winds gusting as well. That's probably a good indication. For non-convective wind shear, you see the WS, that's wind shear expected, at what altitude, what direction, and at what speed. Some other sources you can find wind shear are winds aloft and prognostic charts. On the winds aloft, you can look for a change of direction or wind speed in a short distance or within a few thousand feet. If you see high winds a few thousand feet above the ground, that's also a good indication. On the prognostic chart, I mentioned this before, but if you have closely spaced isobars, that's a really good indication there might be wind shear. And then we also have airmets, sigmets, and pyreps for forecasts and reports. Now, as far as dealing with turbulence, if you ever encounter severe turbulence, do your best to maintain level flight. Things like speed and altitude will vary. All you can do is try to maintain light control pressures and do your best to stay below maneuvering speed. Moral of the story is, with turbulence wind shear, turbulence sucks. You will be flying through it. That's just weather. But hopefully now you know what to look for and how to avoid the really bad stuff. If you've made it this far, thank you. Hope it hasn't been too boring for you. Everything we talked about has been split into nice little sections. In reality, the weather you see and fly in is all mixed together. You might be battling wind shear, mechanical turbulence, and thermals all at once on your approach. You might not even be able to identify a cloud if it's embedded in other clouds and there's a rain shower. However, now that you have the basics down and understand some of the reasons for the why behind why weather happens, at least you'll now know what to expect. And speaking of knowing what to expect, let's talk about aircraft performance. You might be aware that we use what's called a standard atmosphere, and this is based on the temperature of 15 degrees Celsius and 2992 inches of mercury at sea level. Our temperature decreases by 2 degrees per 1,000 feet, and the pressure decreases by 1 inch per 1,000 feet. Anytime it's different than those standard numbers, we have to use corrections. And you know when things aren't standard, pretty much every single day. When we look at some of our performance charts, there will be a reference to ISA, or International Standard Atmosphere, and then some correction for non-standard atmosphere. So let's look at this real quick. Say you're trying to find your fuel consumption at 6,000 feet with an RPM of 2,300. What's standard temperature at 6,000 feet? If it decreases by 2 degrees per 1,000 feet and we start at 15 degrees at sea level, that would be 3 degrees at 6,000 feet. And if your winds aloft say the temperature is 23 at 6,000 feet, you would use this number. Make sense? Remember also our unequal heating thing? Air at different temperatures has different densities or pressures. Our altimeters measure air pressure and show it to us as altitude. And this is why we should periodically set our altimeter on cross-country or longer flights, or you might be doing something like this. And another performance thing is density. It's one of the only things that your airplane has feelings about. Density altitude is the altitude the airplane feels it is at and will perform accordingly. Hot air is less dense, humid air is less dense, high altitude is less dense. So you might be at a 2,000 foot elevation airport, but if it's hot and humid, the actual density of the air might be equivalent to 4,000 feet. And when it comes to your airplane, that's a lot of feelings. Less lift, less thrust, less engine performance. It's going to take you more distance to take off and land, and you'll be coming in to land at a faster ground speed. And I'm saying all of this because you should be looking at your performance on every flight. Density altitude is no joke, and airplane feelings matter. And this is a video here showing just that. It's a high elevation strip on a hot day with a high density altitude. Now let's transition to a more happy topic, if you will. Have you ever wondered why we measure pressure in inches of mercury, and why 29.92 specifically? Couldn't it be like a nice round number? Turns out, back in 1640, the only big thing happening in Italy was this church getting started. It ended up taking 30 years to get built. But instead of jumping in to help, this guy decided to go weigh the atmosphere. I mean, what better way to skip out on the hard labor? He took an empty glass tube, flipped it upside down, and put it in a dish of mercury. On average, the atmospheric pressure would push the mercury up 760 millimeters, or, as you might have guessed, 29.92 inches in freedom units. Later on, a guy named Pascal did some more experiments, and now we have hectopascals as units, which also equal millibars. I will say inches are a weird measurement for pressure, but the equivalent to that is 14.7 pounds per square inch, and that's how much the atmosphere weighs all the way out into outer space. It's not much better than inches either, to be honest. Now, the other question I had was, why not use something like water? And that's because Torricelli here would have needed a 35-foot glass tube, and then we'd have to set our altimeter to 31 feet and 8 inches or something. Turns out mercury is really dense and liquid at room temperature, so much smaller tube. And back then they didn't know about the harmful vapors and all that stuff. Anyways, that's why inches and mercury. I want to finish with a bit of a thought experiment. You think with all these decades of weather observation, research, monitoring, and fancy supercomputers, we'd be able to get a decent forecast, right? Why are meteorologists and forecasts so wrong? You may have heard of the butterfly effect, but in case you haven't, it's the idea that small, seemingly trivial events can have huge consequences later down the line. And the story goes that a butterfly flapping its wings can change the initial conditions of a weather system, and over time, one small event leads to another, and then another, and after enough of those, it leads to a giant thunderstorm. So then, did the butterfly cause the storm? The key thing that the scientist who came up with the butterfly effect was trying to say is that there are so many small, tiny changes, and we can't track them all to see the progression from one event to the next. And we simply don't have the ability to measure all of the complexity and intricacy of nature. So many of these minute variables can cause lots of changes down the road, and millions of them happen on a daily basis. All I'm trying to say is that weather forecasting is very difficult. Now you're at a point where you have a bunch of puzzle pieces and you can kind of start to piece things together. A lot of times we don't even know the pieces that we're trying to fit, and more importantly, how they all interact once we put them together. Meteorologists all get the same weather data from the various weather sensors and observations that we have. The best they can do is guesstimate what will happen based on the previous patterns in their areas. Now, on the big scale, the national weather can be fairly accurate up to about a week. And generally we can predict where the fronts and pressure systems will end up within a couple hours or so. Now on a smaller scale, people generally care about the minute things like how much rain are we going to get, or what time will that start? Beyond about a 3-day forecast, the millions of variables are so unpredictable that even the best supercomputer will probably be wrong. Maybe not completely wrong, but by a big enough margin that we will notice. And that's enough philosophy for a weather video. Thank you for sticking around all the way to the end. If you leave some constructive criticism, don't be surprised if it takes me another couple of years to make a video. And on that note, have fun, fly safe, and always keep learning. See you next time.